Hello and welcome to today's class. For today's class, we'll be considering the modulus of a complex number. Um, given a complex number z, let's say being equal to a plus ib, the modulus of the complex number z is written as this, and it's equal to the square root of this term squared, that's the real part squared, plus the coefficient of the imaginary of the I here, that becomes b squared. All right, so this is how we express the modulus of a complex number. All right, so this sign represents modulus. It's called either the modulus or the magnitude of a complex number. We'll take an example and see how this works. So example 1, let's say we have z is equal to minus 1 plus 14i. And I'm asked to find the magnitude of z. This will be equal to the square root of this term, that's minus 1 all squared, plus this term here, 14 all squared. So here is equal to the square root of minus 1 squared is 1 plus 14 squared. Let's get this done. 14 squared is equal to 19196. 14 squared. This is equal to the square root of 197. So hence, the modulus of z is equal to root 197. So this is how we get modulus of a complex number. A second example, let's say we have the complex number z being equal to minus 1 minus I, and I'm asked to find the modulus of z. The modulus of z, that's z, is equal to the square root of this term, minus 1 squared, plus the coefficient here is minus 1 all squared. So if I work on this, this is equal to the square root of minus 1 all squared gives you positive 1, plus minus 1 all squared gives you positive 1, and that's equal to the square root of 2. So this is how we get the modulus of a complex number. All right, let's proceed. So take a sample problem on modulus of a complex number and see how we can get this done. All right, so this question says if z is equal to 2 over 3 minus 7 over 8i, find the modulus of z. So this is as simple as we said, the modulus of z would be equal to the square root of the first term there. That's the square root of the first term there, 2 over 3 all squared, plus the next term there is minus 7 over 8 all squared. This is equal to the square root of 2 squared is 4, 3 squared is 9, plus minus 7 all squared is 49 all over 8 squared is 64. So if I do this math, you just punch this directly. I'm punching this directly with my calculator. That's 4 over 9 plus 49 all over 64. That's about the square root of 697 all over 576. So I have this. Perhaps in 2dp, I would have, I'll have 1.10, or let's say 1dp, about 1.1. So that's your answer. This is how you get the modulus of a complex number. All right, so this is how this is done. We'll take one more example on this, and then we'll do something else. All right, a final question on modulus of vectors or on modulus of a complex number. It says if z1 is equal to 1 minus I and z2 is equal to minus 2 plus 4i, evaluate z1 plus z2 minus 1 all over z1 minus z2 plus 1 in the form a plus ib and evaluate its modulus. My first task here is to get this expression z1 plus z2 minus 1 all over z1 minus z2 plus 1. If I substitute values, z1 is equal to 1 minus I plus z2 is minus 2 plus 4i, then next up plus minus 1, so minus 1 all over z1 1 minus I minus z2 minus 2 plus 4i, then plus 1, so plus 1. I have this. So evaluate this. What do we get? Taking off the brackets, I have 1 minus I, plus minus is minus 2, plus plus is plus 4i, finally minus I, all over 1 minus I, minus minus is plus 2, minus plus is minus 4i, then plus 1. So I have this. Working on this is equal to, take out the real parts, 1 minus 2 minus 1 minus 1 gives you minus 2. So all the real parts in my numerator gives me minus 2. Take out the imaginary parts, minus I plus 4i gives you plus 3i all over. For denominator, take out the real parts, 1 plus 2, that's 3 plus 1, that's 4, minus I minus 4i, for imaginary part gives me minus 5i. So I have this value. But we are asked to express this one here in this form, a plus ib. So hence, if I have this, I'll have to rationalize. And that's equal to, rationalizing, we have minus 2 plus 3i all over 4 minus 5i. We have to rationalize, simply multiply numerator by the conjugate of denominator, 4 plus 5i all over this one here, 4 plus 5i. So I have this one here. So this is equal to, use the first term here, minus 2, multiply everything here, 4 plus 5i. Use the second term, plus 3i, multiply everything here, 4 plus 5i. So we have this here, all over, use the first term here, 4, multiply everything here, 4 plus 5i. Second term here, minus 5i, multiply everything here, 4 plus 5i. So I have this. All right, so in expansion, what do you have? Expanding this, minus 2 times 4 is minus 8, minus times plus is minus, 2 times 5 is 10, bring down your I, plus 3 times 4 is 12, bring down the I, plus plus is plus, 3 times 5 is 15, I times I is I squared. So we have this all over. For denominator, we have 4 times 4, 16, 4 times 5i gives you 20i, minus 5 times 4 is minus 20i, minus times plus minus, 5 times 5, 25, I times I squared. So I have this. So work on this. This is equal to, I have here as minus 8, minus 10 plus 12 is plus 2i, plus 15 into I squared. We said the value of I squared is minus 1 all over, this is 16, plus 20 minus 20. They will cancel each other. So I'm left with minus 25. I squared, we said, is minus 1. All right. So this is equal to, I'm having minus 8 plus 2i plus minus 15. That's minus plus 15 times minus 1. Minus 15 all over 16 minus 25 times minus 1 is minus 25. So I have this. If I work this out, take out the real parts here. Minus 8 minus 15. That's about minus 23 plus 2i all over 16. Minus minus is plus. It becomes 16 plus 25. That's 41. So hence, this will be equal to minus 23 over 41 plus 2 over 41 all into I. So we've gotten the value of this. Our next task, or we've expressed this one here in the form A plus IB, which is this. Our next task is to get to next up, we have to find the modulus. So find the modulus of z1 plus z2 minus 1 all over z1 minus z2 plus 1. Let's evaluate the modulus of this. All right. So the modulus will now be equal to the square root of minus 23 over 41 squared plus 2 over 41 all squared. So let's get this done. This is equal to, let me get my calculator. That's equal to the square root. Make this bigger. The square root of 23 squared is 529 all over 41 squared is 1681 plus 2 squared is 4 all over 41 squared is 1681. So if I sum this up, same denominator, I'll be having the square root of 533 all over 1681. So I have this one here. Let's see the value. Square root of 533 all over 1681. So that's about, okay, let's see if we can get this one here in surd form. In its simplest form, this is equal to the square root of 13 over 41. So if I have this now, we can still rewrite this as being equal to root 13 all over root 41. So I have this one here. Now we know fully well that we cannot leave, just like we cannot leave the denominator of a fraction as a complex number, we cannot also leave the denominator of a fraction as a surd. So in this case, I'll have to rationalize the surd. So rationalizing the surd, so let's rationalize surd. Rationalizing surd would have that root 13 all over root 14. To rationalize a surd, all over root 41. To rationalize a surd in this form, you simply multiply numerator and denominator by the denominator. That's it. So multiply numerator and denominator by denominator. That's equal to root 13 times 41 is 533 all over root 14 times root 41 times root 41 gives you 41. Hence, my answer is equal to 1 over 41 root 533. These two are the same thing. All right. So this is how we solve this question. All right. So let's look at the conversion of a complex number from one form to another. Now, recall that in our previous lesson, we talked about a complex form being expressed in two forms, z equal to a plus ib, or perhaps ab. We said this is the rectangular or Cartesian form. We talked about z being equal to r into cos theta plus I sine theta. We call this the polar or the circular form. 3, we talked about z being equal to r exponential I theta, and we call this one the exponential or the Eular's form of expressing complex numbers. So let's see how we can convert one complex number from one form to the other one. For instance, before you do conversion of a complex number, note the following. Note that r, we said, is the modulus of the complex number, is given by a squared plus b squared. So this is how we get the value of r. Also note that tan theta is equal to b over a. So we can get theta by taking tan inverse. Tan inverse of b, that's the imaginary part, all over a, that's the real part. So that's how we get this one here. So it's more like saying theta from here. Theta is equal to tan inverse of b over a. So we have this. One last thing, note that theta can be expressed in degrees, that's this, or pi, that's this. All right, in degrees or pi, where 1 pi is equal to 180 degrees. All right, so we have this. All right, so with this one taken, let's try an example. So example, okay. So if you've gotten this, let's look at an example. Let's say we are given, all right, example, let's say we are given the complex number z equal to 4 plus 3i. So this is in rectangular form. Number 1, express this one here. Express this one here in polar form or circular form. Express this one here in Eular's or exponential form. So first things first, let's get r. So r is equal to the square root of this one here, 4 squared plus this one here, 3 squared. That's equal to the square root of 4 squared is 16 plus 3 squared is 9. So hence r is equal to the square root of these two combined gives you 25. So r is equal to 5. We've gotten the value of the modulus as 5. Let's get the angle or the amplitude. The amplitude theta, we said, is equal to tan inverse of b over a. Given this complex number here, b is equal to 3. That's the coefficient of I here. And a is equal to 4. I have this. All right, so this is equal to tan inverse of b, that's 3 all over 4. So that's equal to tan inverse of 3 over 4 gives you 0.75. 0.75. So that's equal to tan inverse of 0.75. We have 36.8 87 degree. So that's theta. So therefore I in polar form z is equal to, we said r, which is 5, that becomes 5 into cos theta here is 36. Perhaps I want to use a round bracket, so I'll change here to a square bracket. Cos 36.87, okay, plus I sine theta there is 36.87. So we have this. All right. So this becomes the complex number in polar form. Finally, II. Let's get this in Eular's form. In Eular's form, what do we have? We said in Eular's form, z is equal to r, which is 5 exponential I theta. So exponential I theta is 36.87. So hence, we can leave it this way, or we can say that's equal to 5 exponential 36.87 I. All right, so this is how we solve this. So this is how we do the conversion of complex numbers from one form to another. All right, so look at the next task. Hello and welcome to today's class. For today's class, we'll be looking at Argand diagram. Argand diagram, we've looked at 3 ways of representing complex numbers: rectangular, Cartesian form, Euler's or exponential form, then polar or circular form. There's yet another way of representing complex numbers known as using the Argand diagram. It's also called the graphical method of representing complex numbers. All right. So what's an Argand diagram? An Argand diagram is simply a graphical method used to represent complex numbers. Now, how does it work? Remember that when it comes to your rectangular form of complex numbers, you have z being equal to, let's say, a plus ib, and we said this is the same thing as a and b. For this case here, this a becomes your x, y, b becomes perhaps your y-axis. So don't forget that in a normal Cartesian coordinate such as this, there are 4 coordinates here, or 4 quadrants: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now, for this one here, this axis is called the I-axis. So I'm having positive I, no longer y now, but I. Here becomes the negative I. Here becomes your x-axis. Here becomes your negative x-axis. Of course, here's a positive x-axis, and here is negative x-axis. So it means if I have a complex number that is positive for x and positive for y, it will be in this region. So this is the region of positive x and positive I value complex number. This region here is for this is negative x, so a negative x value or a negative a value and a positive I value will be in this region. This region is for negative x value and negative I value, while this region here is for positive x value and negative I value. We'll just take a few questions and we'll see how we plot an Argand diagram. Let's say I'm giving the complex number z equal to 3 plus, let's say, 2i. If you observe here, the x value is positive and the I value is also positive. Positive, positive, that's this side here, positive x, positive I. So hence, my Argand diagram for this would be something of this nature. Here, something like this. For the x, this positive x-axis, we said we have 3. That's the a value, 3. So having 3 here. So this is 3. And for the the I, this is the I region, positive I of course, I have 2. So perhaps 2 somewhere, here 2. So where the 2 and the 3 meet, excuse me. All right, so I'm having the positive 2 here, that's this, and the positive 3 here, that's this. So perhaps they meet at this point. So from this point, I'll draw a straight line. So this is simply the Argand diagram. There are more things to add to this, like the modulus will be here and the amplitude will be here. But this is like the concept of drawing Argand diagram. We'll take one more example. Let's say we're given z is equal to minus 4 plus 3i. But to sketch an Argand diagram for this, the Argand diagram for this would be, I'm having a negative x value and a positive I. So I'll come back to this. Negative x, that's this way. Positive I, that's this way. So I'll be drawing quadrant 2 that looks like this. All right, so I'll be drawing quadrant 2 here. Something of this nature, like this, such that I'll be having my positive I value and my 3 somewhere here, and then your negative x value, and perhaps the 4 here. So this becomes a minus 4 because it's a negative x value. So I'm having this, okay, and then this one here. All right, so please, this is a board sketch. So meet somewhere, let's say here. Now draw this way. All right, so this becomes the value of the amplitude. Your modulus will be here. So this is the Argand diagram format. One last thing there. Let's say I'm giving z as equal to minus 11 minus I, for instance, and I want to do the Argand diagram sketch. What do? If I look at this, this is a negative of x and negative of I. Negative x, negative I, this is the quadrant, this one here. So you can see the motion, the way of drawing this, like this and like this. Negative x, negative I. So I'll come here, I'll draw this way and then this way. So I'm having this here. This is negative x, this is negative I region. Negative x, we said we're having here as minus 11. Negative I, we're having here as minus 1. So if we draw them together, we'll be having something that looks like this. So from here, try to join them, we're having something of this nature. Sorry, this line is bent. Let me draw a better line. So minus 11 and minus 1. So we'll have something that looks like this. Theta would be this, and R would be this. So this is what the Argand diagram would look like. Please notice that for an Argand diagram, let's take an Argand diagram. For an Argand diagram, note that you need the values of the x and the I. You also need a value of the amplitude, theta, and then the modulus R. And then you can now get the full form of the Argand diagram. So this is how an Argand diagram works. We'll take a question and try to draw the Argand diagram. All right, so let's look at this question on the Argand diagram. It says, given that z is equal to 1 plus I, find number 1. You have that. That means the modulus or magnitude of z. It says find z in polar form, I. Find z in Eular's form, IV. Draw the Argand diagram of z. All right, so what do we know? Number 1, we know that this one here means magnitude. And we said magnitude is same as R, which is equal to the square root of, the coefficient here is 1, so it becomes 1 squared plus the coefficient here is 1, that's 1 squared. So this is how we get magnitude. So hence R is equal to the square root of 1 squared is 1 plus 1 squared is 1, that's equal to root 2. So here's the value of R. Next, obviously, we have to find z in polar form. To get the value of z in polar form, we need what's it called, the amplitude. And we said amplitude theta is equal to tan inverse of the coefficient of I here, which is 1, all over the real part here, which is 1. So theta is equal to tan inverse of 1 over 1 is 1. Hence, theta is equal to tan inverse of 1. That's about 45 degrees. Remember that we said we can express theta in terms of degrees or in terms of pi. So theta is equal to 45 degrees is equal to, in pi, we said pi is 180. So in terms of pi, becomes pi all over 4. The idea is that 180 divided by 4 gives you 45. That's it. So 180, pi is 180. So 180 over 4 gives you 45. That's how we express this one here in terms of pi. To get the pi value, this is what you do. You just come here. You just say pi all over x equal to 1, equal to theta value, that's 45. All right, just take this one as x. Pi over x is equal to 45 degrees. If you cross multiply pi times 1, pi equal to 45 times x is 45x. But we said pi is 180. So change here to 180, divide by 45, divide by 45. This will cancel this, x is equal to 4. That's how you can easily get that. So it becomes 180 over 4 gives you 45. This is how to get the 4, all right? Pi over an unknown number is equal to the gotten angle. Cross multiply and find x. Our value here is 4. So therefore, II in polar form, therefore in polar form, we have that z, we said in polar form z is equal to r into cos theta plus I sine theta. So that means z is equal to r is root 2. So root 2 into cos theta is 45 plus I sine theta is 45 degrees. So I have this. All right, so this is the value in polar form. We can still work with pi. In terms of pi, that's equal to root 2 into, I'm having cos, so it becomes cos 45, we said, is pi over 4 plus I sine 45, we said, is pi over 4. This still works. So this is the polar form in terms of degrees. This is the polar form in terms of pi. I says in Eular's form, I in Eular's form. In Eular's form, don't forget we said in Eular's form, z is equal to r exponential I times theta. So hence, in Eular's form, z is equal to r, that is root 2 exponential that's equal to r is equal to root 2 exponential I times theta is 45 degrees. So that's equal to root 2 exponential 45i. This works. Or in terms of pi, that becomes root 2 exponential I pi is 45 is pi over 4. This also works. All right. So this is how we express this in Euler's form. One last one, we ask to find or draw the Argand diagram. So let's get the Argand diagram. I'll simply take this one off and draw the Argand diagram here, and that'll be it. All right, let's get Argand diagram for this. So if I look at this question here, this is positive, this is positive. Positive, positive, this is I'm using quadrant 1 of the Argand diagram. So it becomes quadrant 1. So IV4, the Argand diagram, I have this one here, and then this one here. So this is my positive I, this is positive X. The value is 1. I'm having 1 here. This is having 1 here. So 1, 1. So 1 at this point. This is 1. Positive 1 for the coefficient of I. Also I have here as positive 1. So positive 1, positive 1. All right, let's get a line. So a line running from here to that point there. Something of this nature, like this. All right, so that's my thing there. The value here should be R, and we've gotten our R as √2. So √2 will be here. And finally, the angle here we said is the amplitude theta, which we got as 45. So I'm having 45 degrees. So this is how I draw the Argand diagram for this question. All right, so this is how we work with Argand diagrams in complex numbers. We'll take one last example and we're done with this. So we look at a final example on Argand diagram. This question says, draw the Argand diagram of, you have I, Z being equal to 6 minus 2I, and Z equal to minus 18 plus 7I. So I'll do the first part and you attempt the second part. For the first part, solution, for I there, I have Z being equal to 6 minus 2I. We have this. If I want to get an Argand diagram, of course, I will need these two values which are given. I also need the value of the modulus and of course theta. So let's get the value of the modulus and then theta. For this one here, we said the modulus R is equal to the square root of d squared, that's 6 all squared, plus d squared minus 2 all squared. So R is equal to the square root of 6 squared is 36 plus minus 2 all squared gives you 4. That's equal to √40. All right, so that's the value of the R here. √40, can it be broken down? Yeah. R is equal to √40 is √4 times 10. That's equal to √4 times √10. So R is equal to √4 is 2 times √10. That's 2 √10. So R is 2 √10. Let's get theta, the amplitude. Theta, we said, is equal to tan inverse of the B part, coefficient of I, which is minus 2. So minus 2 all over the A part, which is 6. All right, so let me get my calculator. So I have theta is equal to tan inverse, I'm punching this directly, tan inverse of minus 2 all over 6. I'm having the answer as negative 18.43 degrees. We'll leave out the negative. The negative is only showing direction, that it's going to the negative axis of the y. It becomes 18.43 degrees. You can leave out the negative, only shows direction, that it's going to the negative part of I. So finally, my Argand diagram, if I look at this, I have, remember we said this is x and I have a positive x and a negative I. So if I look at this, it becomes quadrant 4, which is positive x and negative I. So I'll sketch this one here. So I'll now sketch this. So my Argand diagram becomes this, positive x and negative I. So I'll label this as negative I, I'll call this as positive x. Negative I is, positive x is 6. So somewhere around here, I'll call this 6. What negative I is minus 2. So somewhere around here, I'll call this a negative 2. So look at their point of intersection, here and this one here. So they intersect at this point. So join this to the origin. So from my origin, I'll try to join these two. It becomes this one here, this right. So I have this one here. All right. The theta is always angle of inclination between arrow. So this is arrow. We said arrow is what there? Arrow is 2 root 10. This is 2 root 10, this value here. Theta is always angle of inclination between the modulus and the horizontal. So it becomes this one here. So modulus and horizontal becomes this. This value we said is 18.43 degrees. So observe, we took out the minus, and I said minus means theta is going to the negative region of I. That's why you have the minus. So I have this as my Argand diagram. This becomes the Argand diagram we are required to get. All right, so that's how we solve this question. Before we leave, please, let me show you some, please. If I have this one here, I have a line here, theta will be here. In this case, theta will be here for quadrant 1. So between the modulus and the horizontal, theta will be here. For quadrant 2, if I have a line like this, theta will be this one here. This is what theta will be between the modulus and the horizontal. If I have for quadrant 3 here, and I have this line here, theta will be this way, please, here, between modulus and horizontal. Finally, for cases of quadrant 4, like this, theta will be here between modulus and horizontal, just as we have in this case. So see where I place theta here. All right. So this is how we solve problems involving Argand diagram. See you in the next class. Please make sure you do this one here as a trial. Test yourself with this, and then, of course, see you in the next class.